Good morning, everyone. I am Priyanka Sisodia on behalf of Mathematics
Deepak
Department.
ji. Hello.
Medicaps
Hello.
Good morning, everyone. I am Priyanka Sisodia on behalf of Mathematics Department, Medicaps University. Warmly welcome our Honorable Vice Chancellor, Dr. Dilip K. Patnaik, Medicaps University, Pro-Vice Chancellor, Dr. D.K. Panda, Medicaps University, respected deans, HODs, and all faculty members and participants. It's my immense pleasure to welcome our speaker of today's lecture, Dr. Santanu Manna. Now, I would like to invite Dr. Deepak Patidar to introduce the speaker.
A very good morning to all and all present here. Welcome to all. I am Dr. Deepak Patidar, Assistant Professor Indore. Dr. Santanu Manna is Assistant Professor at the Department of Mathematics, Indian Institute of Technology, Indore. Prior to that, he spent around 1 year as Newton International Fellow by the Royal Society UK at the School of Mathematics. Indian Institute of Science, Education and Research, Kolkata during SM Dhanbad in 2015. His research interests include partial differential equations, elastic wave propagations, geomechanics, seismic data science, and earthquake statistics. He has published more than 26 referred journal papers of international repute with SCI journals. His publications have more than 339 citations with I-10 index 12 and H-index 10, Google Scholar, January 2022. He has been achieved prestigious fellowship awards like Newton Baba International Fellowship by the Royal Society, UK, and SERB GOI in 2018. National Postdoctor Fellowship by SERB GOI in 2016. And Dr. D.S. Kothari Postdoctor Fellowship by UGC GOI in 2016. He has served on review boards for more than 25 scientific journals, including Scientific Reports, Mathematics and Mechanics of Solids, Mathematical Methods in the Applied Sciences, Applied Mathematical Modeling, JAME, Journal of Applied Mathematics and Mechanics, International Journal of Geomechanics, etc. And also served for scientific committees of various national and international conferences. He also has experience to expose his research innovations in United Kingdom, Russia, Spain, USA, Brazil, etc. I welcome our honorable speaker, Dr. Santanu Manna, on behalf of Medicaps University, Indore. May I request our eminent speaker presentation, please.
Okay, thank you, Dr. Deepak. Am I audible clearly?
Yes, sir, you are audible.
Okay, very good. Thank you so much for the confirmation. Let me share my screen. Yeah. Can you confirm whether my screen is visible or not?
Yes, sir, your screen is visible.
Okay, and it is full screen, right? Full screen mode. Yeah.
Okay, sir, you may proceed.
Thank you so much. Okay, so this is probably my first lecture in Medicaps University. Okay, so maybe once the situations will be improved, that time maybe I can go for in-person visit and interact with the faculty. And yeah, I'm extremely sorry that we are getting delay around 10 to 15 minutes because of the technical issue, and it is generally happening once we'll arrange some kind of general talk in online. So sometimes different institute have a different kind of online platform they are using, so the faculty is not familiar. So yeah, plus minus things have to be managed. Yeah, so thank you very much for your presence, for waiting for 10 to 15 minutes. Okay, so without further delay, I think we can concentrate to our today's session. And yeah, as per the discussions with Dr. Deepak, that I came to know that this semester your institute BTech student, they are taking the course of numerical methods. So he was he actually requested to me to include something on the numerical methods things, although I'm not the expert, exactly the core expert of the numerical things, but I'm trying to explain which will be the effective to the BTech student. Okay, so once we will think about the numerical analysis or numerical methods, we look into the first thing that the data. The data in present world is a big challenge. Accumulation of the data, working with the data, and obviously once the thing is coming to work with the data, the analysis will be there, the process are there, but the process that will be followed by the numerical methods, a numerical process. Okay, how numerically, how you can implement, how you can get the better result, how you can minimize the error, okay, and how you can prove that your result is a sufficient result, okay, to show and to improve the scientific domain, the particular domain where you are working. Okay, so indeed today we are going to talk about the numerical interpolations. Okay, obviously I used here the engineers because the problems that is coming from the engineering domain, they are mostly handled by the numerical solutions. Because let me introduce what exactly the numerical solution and analytical solutions. There is a gap between the numerical and analytical solutions. Analytical solutions will give you the exact solution always. Okay, you will get a exact result of some kind of, if you have some kind of system and you are going to solve that system, you will get the exact result of by using the analytical method. Whereas the numerical methods will give you the approximate result. Then what is the necessary for going for numerical methods? Because in present now, if you go any one of the engineering problem or any one of the real field problem, the problem is not always a linear problem. It's a non-linear problem. But for handling the non-linear problem, either it is an algebraic problem or it is a differentiable problem, okay, geometric problem. For handling a non-linear problem, it is really a difficult task if you have a analytical methods, or analytically if you are going to handle it. So in that case, the numerical method we need to implement, and that will give you a more better result, result to get it at least you can approximate the solutions. Okay, so this is one thing. This is the one of the big reason to consider the numerical things, right? So now let me introduce what is the numerical interpolations. Like what do you mean by interpolations? Interpolations means, suppose if you have some kind of point, say here I have given some point like x0, y0, x1, y2, x1, y1 up to xn, yn. These are the point we have given here. So these are the interpolating point, and I also have given in a graph of those points. You may start from here like x0, y0, x1, y1, x2, y2. These are the points involved there. Now we can calculate also the corresponding value of y1 with respect to this x1. We will also calculate the corresponding value of y2, which is also, we can say, is a function's value of f of x2 and the corresponding value of x2, right? So in that way, we can calculate all the value of this point, the corresponding value at that point. But if we are trying to get one functions containing like this, so you can say that we take some kind of one of the curve which can follow this curve containing all these point. Okay. Now, the numerical interpolations is that you have these kind of points are there. As I have told you that these are the points we have. Now, if you are going to take one curve containing all these points, suppose we are trying to find out the value of that point, value of this point, value of here, then how we can get this value? Because if we compare with the real field, okay, for example, suppose you are trying to calculate some earthquake data, okay, earthquake data from certain time to certain, like 2001 to 2022 in what it's called for example in MP zone, right? And we are trying to find out some kind of range of the data, like see, earthquake data is not a good example. It is not a continuous way. So I can take one one car is moving from your from your beginning to the end. Okay, one car is moving, and there was a signal was there. From there the student can pass. So generally once the car will move from the beginning point to the end point. So there you can see that the speed limiter there, like at the beginning it was I think 40 limit, then to 30, maybe where the zebra crossings are there you can see that the green symbol are there, and then it was showing that the speed limit not more than 20, like that. Okay, so we have some kind of data pointer there. Now we are trying to find out the exact speed in between of these two gaps. Okay, like 30, 40, 50, 10, these are the speed was there. If we are going to find out the exact speed of a particular point in between of these two domains. Okay, so that how we can find out. So new interpolations will give you that kind of result. So for example, here these are the points are there. Okay, you can see we are trying to find out here, somewhere we are trying to find out the value of the particular data. So by using the interpolations, we can find out the value of the data here. Now, here the two things is coming. One is called the interpolations, another one is called the extrapolations. What exactly the interpolations and extrapolations? For example, if you can see that we are trying to find out the value of here, somewhere, like in between of these two domains, like this is the beginning point, this is the end point. Okay, so x0, y0 is the beginning point, xn, yn is the end point. So we are trying to find out the value in between of x0, y0 to xn, yn. Okay, so if you are trying to find out the any one of the value by using the functions, okay, the containing those points, then it is called actually the interpolations. Okay, and if you are trying to find out some value which is beyond the xn, yn, like out of the xn, yn, for example, xn plus 1, xyn plus 1, or maybe here xn minus 1, x minus 1, y minus 1, x minus 2, y minus 2, for example, this side. So out of this domain, that is actually called the extrapolations. So then you can understood that if you have some kind of data, okay, in your domain, you have in your tabulated box, that using the interpolations, you can find out the particular value of the functions inside that box. And if you're trying to find out the value of the functions outside of the box, outside of the domain, then that time you can use the extrapolations. Okay, good. So these are the basic introductions was of the interpolations. Now, as we are starting from the beginning of the interpolations, so let us know how actually the interpolations came out, and where first we can observe about the knowledge of the interpolations. So if you read this book, like one book is there, that is the history of interpolations. Okay, so this Whittaker is a numerical mathematician of Edinburgh University. I think he wrote these books. So these books actually contains the most of the common form of the interpolation occurs when we take a data from a table which does not have a exact value we want. And throughout the history, the interpolations has been used one from the another to justify about the purpose of the under the sums. Okay, now the interpolations came to the ancient Babylon and Greece, where the farmers of the Greece and the Babylons, they were using the time, okay, times for plantations of their crops, okay, based on the predictions of the position of the sun. Like, for example, we know the position of the sun at the beginning, east, from the east side we can get the sun, then at the end of the day we can get it the west side of the sun. So depending on the movement of the sun, okay, if the plantations are there, the plantations need the sunlight. Now farmers know that at which position sunlight will go from there to here. But that time the clock was not there. Okay, so depending on the sunlight, they calculated the interval and they put their plantation. Okay, so that maximum time of the, if the plantation is required a maximum sunlight, so the maximum time of the sunlight they can get this plantation, right? So Similarly, in the China, if you see the China, generally they make a calendar. Okay, so their annual calendar by using the interpolations. So that interpolation actually Newton interpolations formula they generally apply to make their calendars. Okay, and in India, if you think the idea of the interpolations was come from the Greek mathematicians with the Brahmagupta. Okay, so this was the Indian astronomer and mathematician introduced the methods of the second order interpolations, okay, for sine functions, and later the methods are implemented unique, unequal interval of data. So equal interval of data, it has been first investigated, and then it will move to the unequal data point, right? So now, if we see the real example of the interpolations value, like for example, if you are trying to calculate the vibrations of a rail track, okay, train line track, the railway train line track, or maybe some kind of big bridges are there, okay, and if you're trying to get the vibration analysis of the bridges, okay, so then once we are going to calculate the vibration analysis on the bridges or in a track, okay, that is actually the solid media. It's a elastic waves will be there. Like there are two kind of wave are there. There's the elastic wave and elastomagnetic wave. So the elastic wave is there. That is the point by point movement will be there. So that means what? There are grids will be created in that solid bar. So the waves is moving from one grid to another grid, another one grid to another grid, so something like this. So the gap in between of these two grid, okay, either it will be unique gap or it will be a ununique gap. It's maybe the gap will be the unique or maybe may not be unique, right? So but you don't know the end point of the train or track by using the finite difference concept of the finite difference is coming by interpolations, okay. So the using this interpolation techniques, we are getting the finite difference, and using the finite difference we can get the how the wave is moving from the one point to the another one point of that kind of bridges, okay. So it's the same will be applicable if you have some kind of heat you are trying to move from this net, okay. So that how it is movement from one point to the another point. If you are taking another one kind of things like a spring you are taking, okay, and suppose in that spring, the spring is also obviously it's an elastic spring, okay, and this is used to this is also the it has a mechanical energy, okay, and the deflections. Hello, am I audible? I got a message that out of internet. Can you confirm whether I am audible or not?
Yes, you are audible, perfectly all right.
Okay. Thank you so much. Because I got one message that out of internet. Yeah. Okay. I see. So that's why I was telling about the spring that, for example, the deflections is of a spring. We are taking the deflections in x directions, and in a y direction we are taking some kind of load, that is the Newtonian load. Now, if you are going to take a tabulations about the x-axis and the y-axis where the load are there, the tabulating value will give you the interpolating value, which will be in the in the table. Now we can, using that value, we can calculate the the vibrations or the energy resources in the other point inside the domain or the outside of the domain of that. Yeah. Okay, so the basic idea that I already explained about you. Now the one thing is that another one thing is that how we can generate functions in interpolations things, and if some of the cases, if you know that the functions is known to us and some values are there, okay, so using that functions we can make the table, okay. But in some of the cases only we have some points are there, but we don't know about the functions value, what exactly the implicit functions will be there using this point, that we don't know, okay. So that's why there is a explicit, explicit kind of functions are involved there. Okay, how in such case, how we can determine the functions? So that means how we can assume that the curve will be moving in a continuous way and moving from all containing all the points, and how it is moving to the beginning to the end. Now this we can make it out by interpolating by a polynomial, right? How we can make it? For example, if we take some kind of tabulated data which is x0, x1, x0, y0, x1, y1, x2, y2, x3, y3, and xn, yn. We satisfy these relations. For example, one relations we take y is equal to f of x, okay, and which is these are the given where the explicit nature of the functions is unknown, is not there. Then it is possible to construct a similar functions gx, okay, such that this fx and gx, they are well agrees, okay, at the set of the tabulated point. So here are the tabulated points are there, okay, and if we take a implicit functions including this tabulated point, and if we are going to take a similar kind of polynomial similar kind of functions which is gx, we are constructing containing all these points. Okay, now we are trying to find out the gap in between of these two implicit and the functions that we consider. What are the gap in between of them, that we are trying to find out. Now, what criteria decide the best polynomial approximations among these two functions? How, I mean, in using this kind of point, how we can generalize that this is the best polynomial polynomial expressions we can consider. Because the red one, we just consider one is a similar kind of functions involving the green one, which contains the same point. So you can see that at the grid point, where the x0, y0, yx1, y1, these are they are same, but out of there, they may be same, may not be same. So if they are not same, then how we can minimize the gap? So for that, there is an well-known theorems are there, that is called the approximation theory, and that theorem is the theorem is the Oester's theorem. So there, if you see that any functions fx which is a continuous in a closed interval AB, I told you it is continuous in a closed interval AB, and can approximate by a polynomial px, which was considered as a gx, and uniformly over the interval, such that this epsilon is a small epsilon, positive epsilon we consider. So if you take the modulus of the fx and fx and px, that is the approximate polynomial and the function value fx, that would be less is equal to epsilon, right? So this containing this process, we can consider the polynomial. Now, if we think about the polynomial between these 2 points, okay, how we can, what kind of interpolations are there, right? Some points are there in between of some point. If you are going to take some kind of polynomial, like polynomial means if you are connecting from these 2 points by using a straight line, that will give you a polynomial. So this is a, for example, here you can see there are 2 points we have taken. The red 2 points we have taken here. These red 2 points are connected by a lines, right? So this is giving you a polynomial interpolations. Now you can see that it is a global type of interpolating polynomial. So if there is only 2 points are there, so you can draw a straight line, but these 2 points are you can draw a straight line between these 2 points using your interpolating function. Okay, the interpolating functions are there. So using that interpolating functions, you can plot there. For example, if you have a 3 point, so you can take a quadratic polynomial. So that means those 2 straight line you can join in between the first straight line, first point to the second point, then second point to the third point. Okay, so the quadratic functions you can get. And if you have some kind of n+1 points, then by using the n+1 point, you can get a polynomial of degree n, right? So then if you have some kind of n+1 point, you can get a polynomial of degree n. And so this is a global polynomial functions, and this global polynomial interpolating functions is not that much good polynomial. So people generally used to avoid it because of the local maxima and minima issue. okay, and there is a lot of angles are there, right? So if you take some kind of, the straight line between the two point, like n number of point are there, so there is a straight line, here is a straight line are there, so there are a lot of wrinkles you will get, okay, and you don't know about the maxima and minima. So to avoid this kind of wrinkles, we need to take a piecewise linear interpolation polynomial. What the piecewise linear interpolation polynomial they are giving, so they are taking a, the straight line in between of 2 points. For example, here you can see there are 2 pointers there. We are taking one straight line in straight line like this. But here also the another one issue is that here we are taking a straight line, but that is a in between of 2 points, and we are starting from the beginning to the end. We are getting a good polynomial, that is okay. Okay, this is a known, I mean, the function is known in between of the 2 points. Okay, and also yeah, so the yeah, this is this polynomial will give you the piecewise linear polynomial, interpolating polynomial. Why? Because they are connecting the all the points, okay, in between of the two lines. And suppose if they are giving some kind of, for example, if we call this is a G0, this is G1, this is G2, G3, something like this. All the the straight lines are there, which contains the G1, G2, G3, G4, something like this. So this all of this together is called the curve, like y is equal to G of xi. Okay, so this is contains a family of containing the family of straight line, which is Gi, and give a functions which will be in the form of a the general functions. Right now, for the piecewise linear interpolations, there is a derivative is discontinuous. You can see that if you see that here the derivative, here the derivative, these are the discontinuous. Okay, so this is another one issue in case of the piecewise linear polynomial. So to avoid this kind of issue, we I mean the people generally move to the cubic polynomial, right? Cubic polynomial, obviously it is called the cubic spline polynomial, where actually you can get, so the same thing is happening what the piecewise interpolating polynomial was there. But here you can see that if you are going to take the derivative of a function at any point, it is continuous. So earlier cases in piecewise linear interpolations, the derivative was discontinuous, the function was continuous. But in case of the spline interpolation polynomial, you will get the derivative is continuous and the function is continuous as well as the derivative is continuous. Okay, so that's why people generally used to do in real field the spline interpolating polynomial, right? So these are the example of some kind of quadratic spline polynomial, then cubic spline polynomial. So here actually I am giving you the difference between the spline polynomial, cubic spline polynomial, and in general polynomial, right? Okay, one of the real example are there, like for example, if you take one phrase, right, and you are trying to get some kind of line straight, so here you cannot do the any other polynomial other than the spline polynomial, because of cannot go for any other polynomial like a linear polynomial, piecewise polynomial. You cannot go piecewise linear polynomial. Only the spline polynomial you can go, because the smoothness of the phrase. So you cannot get a the flat rectangular triangular shape or the square shape. Okay, so this is actually the this is called the idea is the building of the functions that combined of sum of the basic and simple functions, right? Now, so this was the basic introductions of interpolating polynomial, okay, and where it has been used, those kind of polynomial. Now, let's come to the methods, because we came to know that the use of the interpolations, this is a huge applications. It has everywhere, you can get the applications. Then how we can, what are the methods are there to apply to the problem and get the solution. To applying the method, first of all, we need to know that the points that we have taken, like x0, x1, x2 to xn, whether these points are equal space or unequal space. If it is equal space, then what are the methods? If it is unequal space, then what are the methods are there? Okay, so now you can see in case of the equispaced, that is the equally spaced point, we have a Newton formula and Gauss formula, right? So the Newton has a two formulas. One is the backward formula and was the forward formula. Forward formula means you have some kind of tabulated data and which will move in the forward direction. And if you have a backward formula, then that will be some data are there, but it will move from the backward direction, right? And Gauss interpolation will give you the value of the corresponding value of the function at the center of the tabulated box. Now, in case of the unequispaced, you will get a Lagrange interpolations and divided difference interpolations, right? But it is the benefit is that in case of the unequispaced, the Lagrange interpolations and divided difference interpolations has a great advantage that these are the method which can be applied in both equal and unequal interval, right? So if you are applying a Lagrange interpolation, divided difference in interpolations in everywhere, there will be no problem. Now, in the today's lecture, due to the lack of time, we can concentrate only on the unequispace, because unequispace interval we can have a look, then we can go for equispace interval. Okay, I don't know how much time I can spend for here, because I had instructed to finish it by 12:30. Okay, so I have a lot of slide how you can implement this, forward difference operator, backward difference operator, and central difference operator, average operator, and shift operator. Although, as I came to know that this course is in your basic, BTech courses are there. You are starting this course in this semester, and these are the basic part of the operator. Before starting of the methods, you should have learned those things. So that's why I may give some minimum time to explain those things, and then we can move one table that is called the magic table or the logic diagram, where you can get together all the formula there. Okay, from one table you can derive all the formula. Okay, so I can skip those slides and move on to that. Then if I get later some time, then I'll come back to here and we'll explain from here, right? So these are the operator, right? The forward difference operator, backward difference operator, and then how they are derived in case of the numerical solutions using the table. These are the central difference operator. And if there is an odd number of central difference operator you need and even number of n you have, then there is the formula will be changed over here. And then average the beginning value to the next value by the gap of h. You can move also 2-point value like by the gap of h plus h. So it will be the f of x plus 2h, something like this. Okay, so it was shifting the functions from one point to the another one point. Okay, so these are the basic relations are there among all the operators. Okay, I hope you in your textbook you can get these are the operations among the operators. You can get it. I'm not going to spend too much time here because there is a lack of time, and I get chance once again. Then I will explain next time about this kind of formula, right? How we can implement it. Then also the polynomial I have started from the beginning. So if you take a constant polynomial, then how you can do the operations on the constant polynomial by using the differential operator. So here differential operator are there. So f of x, del of f of x is equal to f of x plus h minus f of x. That is the formula. That is del of f of x is equal to f of x plus h minus f of x. So f of x plus h is equal to a. So that means a is fixed here. And f of a is equal to f of x is equal to also a. So a minus a is equal to 0. Now here also if you take a linear function like a into x, and the differential operator also, you know that f of x is equal to f of x plus h minus f of x, and f of x is equal to ax. So we'll take a into x plus 1, x plus h, minus a into x. That means it will give you a into h constant, right? This is the constant. So in case of the constant polynomial, you will get something like this. If you take the second order operator, then you will get 0 here, right? So same thing also will happen in case of the quadratic polynomial if you take, okay? So the same thing will happen, and in case of the quadratic polynomial, for the first differential operator, you will get a 2hx plus h square, and the second differential operator, you will get 2 into h square, right? Okay, so these are the some kind of derivations of the second order operator I have given, because earlier cases the slide that I skipped, that was the linear operator. In case of the second order operator, how you can derive the functions from here to here, you can see. So these are the known functions, a known value we have. So ultimately the derivation has to go for the known value, then we can get this value of the second order derivative, second order differential operator with y naught. Then the second order differential operator with yn. This is the backward difference, and then the shifting, right? And central is also there. Now these are the actually the formula will work from here. If you see the tabulated value, suppose we are trying to find out the value of x at y, value of y at x. So then the tabulated value you can formulate like this. So you can take the difference between the y1 minus y1 and y2, okay, and that will come over here. The formula already I derived there in that table. So in this way, the forward difference table will go and it will move like this. So here you can see that as it is a forward difference table, so it is forwarding like this: y naught, then del of y naught, then del square y naught, then del q y naught, then del power 4 y naught. So in case of the backward table, it will move from this side. For example, if you see here, it is moving from the end. Okay. So then one thing you can understood that, suppose we are going to find out the value of something at 3.5. Okay. So 3.5 or maybe 3.3 or maybe something 3.1. So that is actually near to the end of the table. So if the value you are suppose trying to find out near to the end of the table, you have to use the, you will get a better result if you use the backward for Newton difference table. Okay, backward Newton difference table, if you apply, then you will get a better result. Whereas if you are trying to find out the value near to the x naught, okay, near to the x naught or near to the x1, that means the beginning of the table, then you can get a better result if you apply the Newton forward difference table, right? So these are the central difference table that I told you if you go for the central part, right? Now here the formulations of the Newton forward formula, how we can derive it, okay, by using the Taylor series expansion. And this is the shifting operator I have taken here. We know that y we can explain as the shifting operator with p. P is given over here. That is the x, the point which we wanted to find out, and this is the initial point, and h, because we are starting from the initial point of the table. That's why we have taken x naught and x minus x naught by h. That will give you the original p. So then you can explain this one by using the relations between the shift operator and the forward operator, and then you can explain the expand these functions by using the Taylor series expansion and get this formula. Okay, so similarly you can also derive the backward difference formula by using the Taylor series expansion. Okay, and that also you can see, you can rewrite in this form like this. Okay, so one thing is that the Newton backward and Newton forward interpolations will give you the good result when the interpolations are done near to the beginning and the end of the table respectively. That I already told, I have written over here, because maybe some internet issue may not hear me. That's why I'm keeping all the text over here. So if you read, then you can understood these things. Now, for better result near to the middle of the table, okay, we need to go for central difference. Okay, so the central difference you can get it a forward, back, goes forward, goes backward, then Starling, Bessel, and invariant formulas are there, right? So now these are the also the Bessel function, how they will move. They will move actually zigzag form. Okay, and formula also we can derive for the case of the Gauss Gauss backward forward formula. That formula actually you can implement it by using the Newton forward formula. So we have to do some kind of calculations, mathematical calculations to come over there. I skipped that calculations. I have given only the original form. Okay, so there is also a chance to move all the the operators to the forward operator only. Okay, so some by using some kind of data arrangement of your table. By using the data arrangement, you can shift all of them in a forward difference operator, and then you can apply one table. You can use one table to get all the formula or to generate all the formula. So here are that table I am giving here. So that is actually called the Logen diagram. Okay, or you can say it's a magic table. So here we are starting from here. You can see that x0 we are taking here. Then above of x0 we are taking x1, x minus 1, x minus 2. Here x1, x2, x3. Right. The corresponding values is also there. Y0. Then y minus 1, y minus 2. Here y1, y2, y3s are there. Okay. Now I do myself some kind of arrangement of some constant over here. Right. What are the constants we have taken? We have taken 1 in between of these two gaps. All in between of these two gaps, we have taken 1, 1, 1. And here we have taken this NC1, right? So in here we have taken as a P plus 2. So I can start from here because I told you that I'll start from the beginning. At a beginning point is the x0 and y0. So I'm taking over here. This is C1, PC1 we are taking. PC1. So then above of PC1, we are taking P plus 1 C1, P plus 2 C1, and here also P minus 1 C1. So actually, I remember to write this formula in this way that I generally put C1, 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 C1 everywhere, then C2, 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 C2 everywhere, then C3, 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 C3 everywhere. Now we'll follow from here, like Y0 I'm following from Y0. Okay, so Y0 I'm making it P. Then above of this, we are increasing by 1, and below of this, we are decreasing by 1. So here also, Y0 is there. I am putting here P. Then above of P, we are increasing by 1 and decreasing by minus 1. So if you go here also you can see the Y0 is P here. Then above of P, we are increasing by 1 and decreasing by 1. Okay. So similarly, we can make the table, whatever the tables we have, data we have, we can prepare the table. And then we can follow in this way that we are starting from the 0, and we can see that in the forward difference Newton forward difference method. Yes, yeah, Newton forward difference. We need to go in forward direction. So I have written over here this symbol actually representing the Newton forward formula, right? So the forward direction, it is moving like this. And this direction is moving on Newton backward formula, right? So these are the symbols I have given here. So it is moving on the backward directions, right? So you can see that my 0, then minus 1, then minus 2 in backward direction it is moving, right? And these are this Gauss forward method. That is the zigzag one. So if you see this symbol like dot dot dot, so that is starting from here, then it is zigzag. Okay. And I'll tell you how they are taking the value, like they will take this value, corresponding value, so that you need to remember. Okay. Then again, if you go for the Gauss backward formula, then it will be also zigzag. So they're starting from by using the star I have given here. So then Starling formula, it will move from here to the end, and the Bessel formula is starting from 1, right? Now, if you write down in a formulas form from the table, then you can see for Newton formula, we are writing that Yp, it is starting from Y0, then PC1 del of Y0. So, and then PC2 del to Y0. So remember these things, and I'll just going to explain from here. So we are taking the immediate above value of this one. So Yp, for using the forward difference, we are writing in this way that Y0 plus PC1 into del of y naught. Then this one is PC2 into del 2 y naught plus PC3 into del 3 y naught. In this way, we are writing. So similarly, once we are writing down the backward formula, we will also write down the y naught plus PC1 into del of y minus 1, P plus 1 C2 into del 2 y naught, y minus 2, and in this way it will move. You can check from here. Okay, the same thing we have written here. Now, in case of the Gauss forward and backward, also we can start from y naught value, nearest value. So that means it is starting from here. So you can see that y naught we are taking y naught plus PC1 into del of y naught plus PC2 into del 2 y1, y minus 1 plus P plus 1 C3 into del Q y minus 1. In this way, it will move. So similarly, in case of the backward formula, this will be y naught plus PC1 into del of y minus 1. So plus P plus 1 C2 del 2 y minus 1. So here it will be the same thing like P plus 1 C3 into del Q y minus 2. Okay. So in this way, we can write down the Gauss formula as well. Now, the central formula, the Starling formula, how we can take? We can take the average of these two values, right? For example, if we start from y naught, we can see in y naught, the above and below value, immediate above and immediate below of this y naught, we are getting something 1 plus 1 by 2. If we move from this way, because this is the Starling formula symbol I have used. So similarly, this one will be PC1 into average of these 2 points. So here also, if you take the sum of this del 2 minus 1 into average of PC2, right? And here also the sum of P3, P plus 1 by P plus 1 C3 into del Q y minus 2, some average of these two value, right? So in this way, we can write down the Starling formula. And Bessel formula also the same procedure will follow as the Starling formula was, like 1 into average of y naught and y1, then del of y naught into average of C1, PC1, P minus 1 C1, and plus PC2 into average of del square y minus 1 and del square y naught. Okay, so in this way you can write down the formula, right? So these are the formula you can derive from this logic diagram. Now another one, now you can think about how you can correlate with the differential operator, because we are using here the differential operator here in the everywhere. So now in case of the Taylor series, you can explain the function in case of the x plus h or x plus h point from x to x plus h. Now if you think about the differential sense, we know that if you are trying to take a derivative of a function, that will be a limit x tends to 0 where h tends to 0 where f of x plus h minus f of x by h, right? So if we think about the Taylor series expansion of the forward difference approximation that we have taken, right, at the beginning of this lecture, middle of the lecture, the forward difference formula, there, if we take up to the linear term and we take the order of h square, h, other part, if we take a order of h, then we can get some formula of the derivative of the function f h minus f of x by h of h. Okay. In case of the backward, you will get something f of x minus h by h plus order of h. In case of the central, you will get something f of x plus h minus f of x minus h by 2h plus order of h square. So the central case, you will give you the better approximation. So that actually brings you to the concept of the finite difference. Okay. So the interpolations concept you have, the interpolation concept is bringing you to the concept of the finite difference. So if you know the finite difference kind of things, then for the engineers, those who are working on the civil engineering or mechanical engineering or electrical engineering, they will get, these are the very, well-known equations you will get there, right? One is called the wave partial differential equation. Another one is called the, heat equations. Okay. So parabolic type equations. There you can apply this kind of concept to get the solutions, because the wave is moving from one direction to another one direction, and the particle is moving from point by point. Okay. So now how you can calculate the grid-wise calculations in between of this point by using the finite difference technique or the interpolations that we derive, we can go and calculate. So from the beginning to the end by the initial conditions. So actually these are the problems. One, you have some kind of initial or boundary conditions will be there. So using the initial and boundary conditions, you can move from the beginning to the end. Okay. So maybe once I'll get the chance to talk about more about the interpolations, then maybe I can try to connect you from the interpolating point to the finite difference point, and the finite difference point will be applied many places of the partial differential equations or the ordinary differential equations, where you can get a real applications, real field applications of your engineering field. Okay, thank you so much. Indeed, I can close my seminar, or maybe I am running in 5 minutes delay. Okay, these are the books are there. So the student, if you are interested, you can go those books. Okay, you can get a good idea. Okay, thank you.
Thank you.
Yeah, Dr. Deepak, over to you.
Yes, sir. Yes, sir. I am audible.
Yes, yes.
Thank you, sir, for giving valuable insights on the topic of implementation of numerical methods for engineers. This is time for question answer session. The first question is asked from the student side. The question is that is the interpolation effective for infinite number of arguments very large? Sir?
Yes. 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 Can you hear me now?
Yes, sir. Here we tell you.
Yes, yes. Obviously, we told you about the extrapolations, right? In case of, if it is an infinite number of things are there, like and now actually some boundary would be there. Like if you have a real problem, okay, you are trying to solve a real problem, some boundary will be there. So within that boundary, you need to get the solutions. In case of the infinite, also you can go for the infinite, but some interval would be there. For example, in a point, you have some 10 points are there. So you are trying to find out the value of the function at the thousandth point. So the thousandth points, you cannot do it by using your own hand. You need to take the help of your software, because basically the numerical methods is another one name is called the scientific computing. In scientific computing, you can use the numerical methods kind of things. So yes, you can get it. So in that case, if you are trying to find out the value at 1000 points, so the 1000 is, in your case, it is infinity, because we have a 10 points are there.
Okay, sir.
Right?
Okay. Okay, sir.
Yeah.
Got it.
And also I do not have time. I actually has a plan to show some kind of demonstration of 5 minutes by using the MATLAB. But yeah, maybe next time I can do it. Okay. I was trying to show how the spline polynomial, in using the spline polynomial, how you can calculate the value and a particular point in between. Okay. Anyway, next time we can see it.
Okay, sir. I got
Yes,
it. This question. The second question is asked from the student side is that how to implement P of X in interpolation in Weierstrass theorem. Sir, you are explaining Weierstrass theorem. What is Px you are showing?
Yes, Px actually you need to consider one function, okay, which will follow the data points. So like let's go to that.
Yes, sir.
Yes. Yes.
This theorem. Yes, sir. This
actually, if you go to here, then you can see that the data points are there. Now, using that data point, if you are trying to use the, you can understood right now that there are three kinds of polynomials are there. One is the linear polynomial. Another one is called the, piecewise linear polynomial, and the spline polynomial are there. Now, if you are trying to take a polynomial which is maybe linear polynomial, which is containing like this, and they may not, give a better approximation. So then how you can judge whether this polynomial or this functions is giving a better functions? So for that, you need to take another one subsidiary functions, from where you can get the better approximation. Better approximation means you are trying to minimize the error. Okay, so here in this case, if this is the f we are taking, and another one functions we are taking polynomial functions, that is p. Okay, so where we are minimize this error. So you can see that the definition was the difference modulus of difference between this f and px will be less is equal to epsilon, where epsilon is very, very small.
Okay, sir.
Okay.
Okay, sir. As we are short of time,
Yes.
we are end the question answer session. I would like to invite Priyanka ma'am. Priyanka ma'am.
Yes, sir. It's time for vote of thanks. So I would like to invite Dr. Pranjali Kekre, in charge of Mathematics Department, Medicaps University. Over to you, ma'am.
Thanks, Priyanka. Good afternoon. I, Dr. Pranjali Kekre, want to give vote of thanks on behalf of the Mathematics Department. Thanks to Honorable Vice Chancellor Dr. Patnaik, Pro Vice Chancellor Dr. Panda, Dean Sciences Dr. Preeti Jain for permitting us to organize this expert lecture. Thanks to the convener Dr. Rekha Jain, Head Department of Mathematics, and the whole organizing team for the arrangement required for the smooth conduction of the lecture. Thanks to co-convener Dr. Deepak Patidar for coordinating and inviting the expert speaker Dr. Santanu Manna. We are thankful to Dr. Santanu Manna for sharing deep knowledge of the implementation of the numerical interpolation technique, including basic knowledge of the spline and the B-spline. The lecture was very interesting and enjoyed by all the faculty members and the student. Hope all of you will use the techniques shared by the sir in your respective fields. Thanks to all faculty members and the dear student for attending the lecture. Thanks to all. Thanks, sir.
Thank you.
Okay, it's time for photography. Please, on the video, all the faculty members. This is the photo session's time. It's okay, Priyanka ma'am?
Sir, wait a minute.
Sir, wait a minute.
Yes, ma'am, ऐसे तो हो गया.
Okay.
Okay, done, sir.
Okay, sir. Thank you for very much for giving our valuable time. May I leave the meeting, Pranjali ma'am?
And sorry for the disturbance at the beginning, and I don't know why it is happening today.
Okay, sir. It's not a problem.
Yeah.
It's happening due to technical. Pranjali ma'am, can end the meeting?
Yes, you can. Thank you, sir.
Thank you. Thank you,
Thank
students.
you, sir.
Okay.
Shall I leave now?